Two spacecraft launched in 1977 are moving through space faster than almost anything else our species has ever built, and neither one has escaped the sun. Voyager One crossed a boundary called the heliopause back in 2012, and headlines around the world declared that humanity had finally left the solar system. That announcement was not quite true. Voyager One did leave something that day, a bubble of solar wind called the heliosphere, but the sun's grip on that spacecraft never loosened, not even slightly. It is still falling under the sun's gravity right now, and it will keep falling for tens of thousands of years before it has any real chance of breaking free. This is why leaving the solar system is not something any spacecraft has ever done, and why the fastest, farthest human-made object in history is still, technically, going nowhere. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. To understand why escaping the solar system is so much harder than it sounds, you first have to understand what the solar system actually is. Because the answer depends entirely on where you decide to draw the line. The sun does not simply sit in empty space, quietly shining. It is constantly exhaling. Every second, it throws off a stream of charged particles called the solar wind, protons and electrons, moving outward in every direction at hundreds of kilometers per second. This wind does not travel forever. It pushes outward against the thin gas and dust that fills the space between stars, called the interstellar medium. And for a long time, the solar wind wins that contest, carving out a vast bubble around the entire solar system. That bubble is called the heliosphere, and it is almost incomprehensibly large, stretching far beyond the orbits of every planet, far beyond the region where comets like Pluto reside, out into a kind of no man's land between our star and the rest of the galaxy. Inside the heliosphere, the solar wind moves outward at supersonic speed, faster than pressure waves can travel through it. But nothing stays supersonic forever. As the solar wind pushes farther from the sun, it thins out, and eventually it slams into the resistance of the interstellar medium hard enough to abruptly slow down. That collision point is called the termination shock, and it marks the first real boundary of the outer solar system, the place where the solar wind stops moving faster than sound and begins to pile up on itself. Beyond the termination shock lies a turbulent, compressed region called the heliosheath, a churning transition zone where the solar wind, now slow and thick, mixes uneasily with the pressure of the galaxy pressing in from outside. The heliosheath is not a thin line on a map. It is a vast, deep layer, and spacecraft have to cross billions of kilometers of it before reaching the true edge. That true edge is the heliopause, the point where the pressure of the sun's own wind finally drops to nothing, and the plasma around the spacecraft switches from being distinctly solar in origin to being distinctly interstellar. This is the boundary Voyager One crossed in 2012, and it is a genuinely meaningful milestone. Crossing the heliopause means leaving the direct influence of the sun's breath, the plasma bubble the sun has been blowing for billions of years. It means becoming the first object built by human hands to sit in the material that fills the space between stars, rather than the material blown outward by our own. That is an extraordinary achievement, and it deserves the attention it received. But the heliopause is a boundary defined by plasma physics, by the pressure of particles and magnetic fields, not by gravity. And gravity is the force that actually decides whether something has left the solar system or not. The sun's gravitational pull does not stop at the heliopause. It does not even come close to stopping there. Gravity, unlike the solar wind, has no edge, no shockwave, no sudden pressure drop where it simply switches off. It fades gradually, following an inverse square law, weakening with distance but never reaching exactly zero, no matter how far you travel. Even a photon of light leaving the sun right now, traveling at the fastest speed permitted by physics, is still being pulled backward, however faintly, by the sun's mass, for as long as it remains within any meaningful distance of our star. So the moment Voyager 1 crossed the heliopause, it had left the solar wind behind, but it had not left the sun's gravitational grip behind at all. It was still orbiting the sun on an extremely long, extremely slow, barely curving path, exactly the way Earth orbits the sun, just on a vastly larger scale and at a vastly slower pace. This is the part almost nobody explained clearly when the headlines ran. There are, in a very real sense, two different solar systems, nested one inside the other. There is the heliosphere, the plasma bubble carved out by the solar wind, which Voyager 1 left in 2012. And there is the gravitational solar system, the region where the sun's gravity is still the dominant force shaping an object's motion, which extends dramatically farther, and which Voyager 1 has not even come close to leaving. The distance between those two boundaries is not small. It is not even in the same category of small. The heliopause sits somewhere in the range of 120 times the distance between Earth and the Sun. The true edge of the Sun's gravitational dominance, the point where a passing star's pull becomes stronger than the Sun's own, lies roughly 2 light-years away, thousands of times farther than the heliopause. In between those 2 points sits an almost unimaginably vast, almost entirely empty region, filled with a sparse, frozen population of icy bodies that most people have heard of but few truly understand, the Oort cloud. We will return to that region because it is the true final boundary of the solar system, and it is also the reason escaping the sun's grip takes so unbelievably long. But first, to understand why our fastest spacecraft still cannot manage it, we need to understand exactly how fast Voyager 1 and Voyager 2 are actually moving, how they got that speed, and why that speed, staggering as it is by human standards, is nowhere near enough. Voyager 1 and Voyager 2 launched within weeks of each other in 1977, timed to take advantage of an alignment of the outer planets that happens only once every few generations. Jupiter, Saturn, Uranus, and Neptune were arranged in such a way that a single spacecraft could visit all 4, using the gravity of each planet to fling itself toward the next, gaining speed at every stop rather than spending it. This technique is called a gravity assist, and it is one of the cleverest tricks in the history of spaceflight. A spacecraft approaches a planet, swings around it on a carefully calculated path, and departs in a different direction, having stolen a small, almost immeasurably tiny fraction of that planet's own orbital momentum. The planet does not notice. Its own enormous mass barely registers the theft, but the spacecraft, tiny by comparison, can gain an enormous boost in speed relative to the Sun, essentially for free, without burning a single extra gram of fuel. Voyager 2 took the full grand tour, sweeping past Jupiter, then Saturn, then Uranus, then Neptune, gathering speed and unprecedented photographs at each stop before curving out of the plane of the planets entirely. Voyager 1 took a more direct route, skipping Uranus and Neptune in favor of a close pass by Saturn's moon, Titan, a target so scientifically valuable that mission planners were willing to sacrifice the rest of the grand tour to get a good look at it. That decision bent Voyager 1's path upward, out of the plane in which the planets orbit, sending it on a steep climb away from the solar system that it has followed ever since. Between the two of them, these spacecraft used the giant planets of our own solar system as stepping stones, borrowing velocity the way a skipped stone borrows momentum from the water it bounces off, and it worked spectacularly well. Today, Voyager 1 is the farthest human-made object from Earth, moving away from the Sun at roughly 17 kilometers every second. Voyager 2, on a different trajectory, moves slightly slower, at around 15 kilometers every second. To put that speed in honest terms, without turning it into an endless string of comparisons, 17 kilometers per second is fast enough to cross a distance equal to the width of a small country in about the time it takes to read this sentence aloud. It is a genuinely extraordinary velocity, one that took decades of careful engineering and a rare planetary alignment to achieve. And yet, at that speed, Voyager 1 has spent nearly 5 decades reaching a distance of only around 25 billion kilometers from the Sun. The scale of what still lies ahead makes that number feel almost small. Both spacecraft are still sending back data, although just barely. They are powered by radioisotope thermoelectric generators, devices that convert the heat released by the slow radioactive decay of plutonium into electricity. There is no way to refuel them, no way to send more plutonium across billions of kilometers of space, so their power output has been declining steadily since the day they launched. And mission engineers have had to shut down instrument after instrument to keep the remaining systems alive. Heaters have been turned off. Backup systems have been disabled. Entire scientific instruments have gone silent, one by one, in a slow, deliberate process of triage designed to keep the spacecraft transmitting for as long as physically possible. Current estimates suggest that both Voyagers will run out of usable power sometime in the 2030s, after which they will fall permanently silent, still moving, still following the exact same trajectory, but no longer able to tell us anything about where they are or what they are passing through. At that point, they do not stop. They do not slow down in any meaningful way, because there is essentially nothing left out there to slow them down. They simply become dark, drifting monuments, continuing to move outward at the same speed they have now, carried by momentum alone for the rest of time, unless something extraordinarily unlikely happens to intercept them. This is worth sitting with for a moment, because it reframes the entire question of escape. Voyager 1 is not struggling against friction, or air resistance, or any force that saps its speed the way those forces would on Earth. Space is close enough to a perfect vacuum that once a spacecraft is moving, it keeps moving, indefinitely, without needing any further push. The only force still acting on it in any significant way is gravity, the Sun's gravity, pulling backward, ever so slightly, on every kilometer of its journey. The question of whether Voyager 1 can escape the solar system, then, is really a single, precise physics question. Does it have enough speed to overcome that pull permanently? Or will the Sun's gravity eventually win, curving its path back inward, the way a ball thrown into the air eventually falls back to Earth? The answer to that question required scientists to calculate something called escape velocity, and understanding what that term actually means, and why it changes depending on where you are, is the key to understanding everything that follows. Escape velocity sounds like a single fixed number, a kind of cosmic speed limit you either meet or fail to meet, but it is actually something far more fluid than that. Escape velocity is the minimum speed an object needs, at a given distance from a given mass, to break free of that mass's gravity forever, assuming nothing else pushes or pulls on it afterward. The important phrase there is "at a given distance," because escape velocity is not constant. It changes depending on how far away you already are. Close to a massive object, deep in its gravitational well, escape velocity is high, because gravity is strong there and you need a lot of speed to outrun it. Farther away, where gravity has already weakened, escape velocity is lower, because you have less of a well left to climb out of. Think of it less like a wall you have to smash through, and more like a hill you have to climb. If you start at the bottom of a steep hill, you need a lot of momentum to reach the top and keep going over the other side. If you are already partway up that hill, you need less additional momentum to finish the climb, because gravity has less work left to do to pull you back. At the distance of Earth's orbit, the speed needed to escape the sun's gravity entirely is a little over 42 kilometers per second. That number sounds intimidating, and it is, but it is the number for an object starting from Earth's distance. Voyager One is not at Earth's distance anymore. It has been climbing outward for nearly 5 decades, and at its current distance, deep in the outer reaches of the solar system, the sun's gravity has weakened enormously. The escape velocity required at that distance is a small fraction of what it was near Earth, because so much of the climb has already been done. This is the piece of the puzzle that makes Voyager One's situation so interesting. It did not need to accelerate to 42 kilometers per second to eventually break free. It needed to have enough total energy, combining its speed and its distance, to guarantee that it would keep climbing outward forever, rather than eventually stalling and falling back. In physics terms, this comes down to a single, elegant question. Is the spacecraft's total orbital energy positive or negative? An object in a closed, bound orbit, like Earth circling the Sun, or a comet swinging in from the outer solar system and looping back, has negative total energy. It is gravitationally trapped, destined to keep orbiting the same central mass indefinitely, tracing the same repeating path around it. An object with exactly zero total energy is on what is called a parabolic trajectory, moving just fast enough to reach an infinite distance with a final speed of exactly nothing, forever slowing, forever approaching zero, but never quite turning around. An object with positive total energy is on a hyperbolic trajectory, moving fast enough that it will not only escape, but will still be moving at some leftover speed, even after gravity has done everything it can to slow it down. Because of the specific combination of speed and direction it received from its many gravity assists, particularly the powerful boost from Saturn and Titan, Voyager One's total orbital energy relative to the Sun is positive. It is, in the strict mathematical sense, on a hyperbolic trajectory. It is not orbiting the Sun the way Earth does, tracing the same ellipse over and over. It is on an open path, one that will carry it outward, away from the Sun, essentially forever, gradually slowing as the Sun's pull continues to tug backward on it, but never slowing all the way to zero and never turning around. In that specific, technical, energy-based sense, Voyager One has already escaped the Sun. It is unbound. It will never return. But here is where the language starts to work against clear understanding. Because being gravitationally unbound and being gravitationally free are two very different things. Voyager One's path is a one-way trajectory out of the solar system, yes, but it is still, right now, and for a very long time to come, deep inside the region the Sun's gravity dominates. It is still slowing down, even now, even after 5 decades, because the Sun's pull, however weak at this distance, has not yet finished acting on it. It will keep slowing, asymptotically, approaching some final cruising speed that it will essentially never quite reach, for as long as it remains within the outer reaches of the Sun's influence. And that region, the region the Sun's gravity still meaningfully dominates, does not end anywhere near where Voyager One currently is. It extends, by most estimates, roughly 2 light-years outward, encompassing an almost unimaginably vast, mostly empty volume of space filled with a scattered, frozen population of debris left over from the solar system's formation, a region we call the Oort cloud. To actually leave the solar system, in the fullest, truest sense, meaning to leave the region where the sun remains the dominant gravitational influence on your motion, Voyager 1 does not need more speed. Its trajectory already guarantees it will get there eventually. What it needs, instead, is time, an almost incomprehensible amount of time. Before we get to that almost incomprehensible amount of time, it is worth asking a more basic question, one that goes to the heart of why escaping the solar system quickly is not simply a matter of building a bigger rocket. Why can't we just launch something faster? The answer lies in a piece of mathematics discovered by a mostly self-taught Russian schoolteacher named Konstantin Tsiolkovsky more than a century ago, long before anyone had built a working rocket capable of leaving the atmosphere. The equation he derived is now simply called the rocket equation, and it describes one of the most stubborn, unforgiving relationships in all of engineering. The rocket equation says that the change in velocity a rocket can achieve depends on two things: the speed at which it expels its exhaust, and the ratio between its fully fueled mass and its empty mass. That second part is the trap. The relationship between fuel and final speed is not linear. It is not the case that doubling your fuel doubles your final speed. The relationship is logarithmic, which means that every additional increment of speed becomes exponentially more expensive to achieve, because the fuel needed to gain that speed also has to carry the fuel needed to lift the fuel that comes before it. Rockets do not just carry payload, they carry the fuel to move the payload, and the fuel to move that fuel, and the fuel to move that fuel, in a spiraling, self-referential burden that grows faster than most people intuitively expect. This is why a rocket capable of reaching orbit is almost entirely fuel by mass, with the actual payload, the part that does anything useful, making up a tiny sliver of the total. Now extend that same problem to interstellar speeds. If you wanted to build a chemical rocket capable of reaching even a modest fraction of the speed of light, the fuel required would not fit on any structure we could ever build. It would not fit in the solar system. The mass of fuel needed would, at a certain point, exceed the mass of the rocket by numbers so large they stop being meaningful, spiraling toward infinity long before you reached any interesting fraction of light speed. Chemical rockets are limited by the speed at which their exhaust leaves the engine. And no matter how energetic the chemical reaction, that exhaust speed tops out at a few kilometers per second. Every gain in the spacecraft's final speed has to be purchased at that same limited rate, which is why chemical propulsion, the only technology that has ever actually launched a spacecraft from Earth, is fundamentally incapable of reaching interstellar cruising speeds on its own. This is the real reason Voyager 1 and Voyager 2 are not moving faster. It is not a failure of imagination, or a lack of ambition, or an oversight by the engineers who built them. It is a hard mathematical ceiling, the same ceiling every chemical rocket in history has run into. The engineers who designed the Voyager missions understood this ceiling perfectly well, which is exactly why the gravity assist maneuvers we described earlier mattered so much. Gravity assists are, in effect, a way of cheating the rocket equation, borrowing speed from a planet's own orbital motion rather than paying for it with fuel carried on board. There is a related trick called the Oberth effect, where firing a rocket engine while deep inside a gravity well, moving at high speed near a planet or the sun, produces a much larger final speed boost than firing that same engine in open space, because the energy added by the engine combines multiplicatively with the kinetic energy the spacecraft already has. Mission planners use both of these tricks together whenever possible, threading spacecraft past planet after planet, squeezing every possible kilometer per second out of gravity before committing to open space, precisely because fuel alone will never get a spacecraft to truly high speed. Even with every trick available, though, the numbers remain sobering. Voyager One's 17 kilometers per second, remarkable as it is, represents only a tiny fraction, well under 0.1%, of the speed of light. At that pace, reaching even the nearest star system to our own would take on the order of 70,000 years, a span of time longer than the entire history of human civilization, longer than the time since the last ice age began to retreat, longer than the entire span of recorded human history stretched out many times over. And that assumes Voyager 1 is even heading toward a star at all, which it is not. It is heading in a direction that happens to carry it roughly toward a star called Gliese 445. And even then, it will only pass within a few light years of it, drifting by in the cosmic dark rather than arriving anywhere. This is the sobering truth underneath the entire question of escaping the solar system. Reaching the boundary is a problem of time and gravity. Reaching another star afterward is an entirely separate, far larger problem of energy, one that no chemical rocket, no gravity assist, and no clever trajectory has ever come close to solving. To understand just how large that boundary actually is, and why crossing it takes so unbelievably long even for our fastest spacecraft, we need to look closely at the region that truly marks the edge of the Sun's domain, the vast, frozen, mostly theoretical shell of debris known as the Oort cloud. Most people, when they picture the solar system, picture the Sun, the 8 planets, maybe the asteroid belt, and Pluto lingering somewhere out at the edge. That picture, comforting and orderly as it is, captures only the tiniest, innermost fraction of what actually belongs to the Sun. Beyond Neptune lies the Kuiper belt, a disk of icy bodies including Pluto, still relatively close by cosmic standards, still roughly in the same flattened plane as the planets. But beyond the Kuiper belt, far beyond it, lies something almost nobody has ever seen directly, something inferred entirely through mathematics and the behavior of long-period comets, a vast, spherical shell of icy debris called the Oort cloud. Nobody has ever photographed the Oort cloud. No spacecraft has ever reached it. Its existence was proposed by the astronomer Jan Oort in the 20th century, based entirely on the orbits of certain comets, the ones that arrive from seemingly random directions, on wildly long, looping paths that suggest an origin far beyond anything we can observe directly. Oort reasoned that a spherical shell of icy bodies must surround the entire solar system at extreme distance, occasionally nudged by the gravity of passing stars or the tidal pull of the galaxy itself, sending the occasional icy fragment tumbling inward toward the Sun, where it eventually becomes visible to us as a long-period comet. The scale of this hypothesized cloud is difficult to hold in your mind honestly, because it is unlike anything encountered in ordinary human experience. The inner edge of the Oort cloud is thought to begin somewhere around 2,000 times the distance between Earth and the Sun. The outer edge is thought to extend out to somewhere between 100,000 and 200,000 times that same distance, reaching roughly 1.5 to 2 light-years from the Sun in every direction. To put the scale of this region in honest terms, the entire zone containing the Sun and all 8 planets, from the Sun out to Neptune, could fit inside the Oort cloud, with room to spare thousands of times over. The Oort cloud is not a wall. It is not a barrier a spacecraft would visibly strike or pass through in any dramatic sense. It is closer to an incredibly thin, incredibly sparse mist of icy bodies, each one separated from its neighbors by distances so vast that a spacecraft passing through the region would almost certainly never come anywhere near any individual object. If you could somehow stand on one of these icy bodies and look around, you would see nothing. No neighboring comets visible to the naked eye. No sense of being inside a cloud at all. Just the same black, star-filled sky as everywhere else, with the sun reduced to a faint, barely distinguishable point of light among countless others. This is the region Voyager One must cross before it can honestly be said to have left the solar system. At its current speed of roughly 17 kilometers per second, reaching the inner edge of the Oort cloud will take approximately 300 years. That is not a typo, and it is not the difficult part. The difficult part comes after. Crossing the entire Oort cloud, passing all the way through its icy, sparse expanse and out the far side, will take Voyager One somewhere in the range of 30,000 years. 30,000 years is a span of time that dwarfs nearly every unit of history humans typically use to measure things. It is longer than the entire span of recorded human writing. It is longer than the time since the earliest known cave paintings were made by our ancestors. It stretches back, if you ran the clock the other direction, to a period when much of the northern hemisphere was still locked beneath sheets of glacial ice, when humans had not yet developed agriculture, when the very concept of a permanent settlement had not yet been invented. Only after completing that entire multi-thousand-year crossing will Voyager One finally reach the true outer edge of the sun's gravitational dominance. The point where the pull of neighboring stars and the broader gravity of the galaxy finally exceeds whatever faint grip the sun still has left. Only then, in the most complete and rigorous sense of the term, will it have actually left the solar system. Everything before that point, every kilometer of the journey so far, including the celebrated heliopause crossing in 2012, including everything it will do for the next several hundred centuries, all of it happens while Voyager One remains, in a very real physical sense, still inside the sun's home. This is the piece of the story that rarely makes it into the headlines, because it does not fit neatly into a single announcement. There was no dramatic press conference for the moment, still tens of thousands of years away, when Voyager One will finally cross the outer edge of the Oort cloud. There will not be one, because by then, the spacecraft will have been silent and dark for tens of thousands of years already, its instruments long dead, its radio transmitter powered down permanently sometime in the 2030s, its final signal already having reached Earth and faded into history long before the true departure ever happens. Voyager One will complete its escape from the solar system as a piece of cold, inert metal and plutonium, tumbling silently through a region of space with no name most people would recognize, unheard, unwatched, and utterly alone. There is another layer to this problem that makes the boundary of the solar system even harder to pin down, and it has to do with the fact that the sun is not sitting still. The sun, along with its entire retinue of planets, moons, asteroids, and the sprawling Oort cloud, is itself in motion, orbiting the center of the Milky Way galaxy at a speed of roughly 230 kilometers per second. A full orbit around the galactic center takes the sun somewhere in the range of 230 million years. A span of time so long that the sun has completed only around 20 of these orbits since it formed. As the sun moves through the galaxy, it does not travel through empty, static space. It moves through a region populated by other stars, each on its own path, each with its own gravitational field, and every so often, over long enough timescales, other stars pass relatively close to our own. Astronomers use the term sphere of influence to describe the region around the sun where its gravity remains the dominant force acting on nearby objects, stronger than the pull of any neighboring star or the general gravitational field of the galaxy as a whole. This sphere of influence is not a fixed, permanent boundary, drawn once and never moved again. It shifts, subtly, as the distances to neighboring stars change over time, as those stars drift closer or farther in their own independent orbits around the galactic center. Right now, the nearest star system to our own is the Alpha Centauri system, sitting a little over 4 light-years away. 4 light-years might sound close in a universe full of unimaginable distances, but it represents a gulf that dwarfs everything we have discussed so far, a distance roughly 40,000 times greater than the entire width of Neptune's orbit around the Sun. Even at that distance, roughly halfway between the Sun and Alpha Centauri, gravitational tug-of-war becomes a genuine, calculable balance point, a place where an object would feel the Sun's pull and Alpha Centauri's pull as roughly equal, technically no longer more bound to one star than the other. Because the Oort cloud's outer reaches extend out to somewhere between 1 and 2 light-years, the true, complete gravitational domain of the Sun brushes up uncomfortably close to the midpoint of that gap, meaning our solar system and our nearest stellar neighbor's own comet cloud, if it has one, may very well overlap at the extreme edges, in a slow, almost imperceptible handshake between two star systems that exchange the odd icy wanderer over hundreds of millions of years. This has an interesting implication for our own history that most people never consider. Stars are not fixed points, and in the deep past, other stars have passed much closer to the Sun than Alpha Centauri does today, some of them close enough to have measurably disturbed the outer Oort cloud, nudging a fraction of its icy residents onto new paths, some falling inward toward the Sun as comets, others flung outward entirely, lost to interstellar space forever. The reverse is also true, and will happen again in the future. Astronomers have identified stars that will, over the coming tens of thousands to hundreds of thousands of years, pass closer to the Sun than any star does currently, close enough to stir the Oort cloud once more, potentially sending a fresh wave of comets falling in toward the inner solar system, an event with no precise, predictable timeline, but one considered essentially inevitable, given enough time. All of this means the boundary of the solar system is not simply far away. It is also, in a slow, geological sense, alive, breathing in and out over millions of years as the galactic environment around the Sun shifts, as neighboring stars drift closer and farther, as the balance of gravitational influence redraws itself again and again, across timescales that make even the Oort cloud crossing time look almost brief by comparison. Voyager One. By the time it finally does complete its slow, multi-thousand-year passage through the Oort cloud, will be emerging into a galactic neighborhood that no longer quite matches the one it left. The stars nearest to the Sun today will have shifted position, some drifting away, others drifting closer. The entire local arrangement of stars, subtly rearranged by the passage of so much time. The same way the arrangement of furniture in a room might shift subtly if you left it alone for 30,000 years and returned to find it slowly rotated by forces too slow to notice happening. Given how badly chemical rockets fail at this problem, it is worth asking what other options exist, because scientists and engineers have spent decades seriously proposing alternatives, some of them almost unnervingly ambitious. The most extreme of these proposals is called Project Orion, conceived in the late 1950s, which suggested propelling a spacecraft by detonating a series of small nuclear explosives behind it, one after another, each blast pushing against a heavily reinforced pusher plate that would absorb the shock and convert it into forward thrust. It sounds almost absurd, and in many ways it was, but the underlying physics held up under scrutiny. Nuclear pulse propulsion could, in principle, achieve exhaust velocities and final speeds far beyond anything chemical rockets can reach, potentially allowing a spacecraft to achieve a meaningful fraction of the speed of light. The project was ultimately abandoned, not because the physics failed, but because of the practical and political problems of launching a vehicle that relies on detonating nuclear devices, along with international treaties banning nuclear explosions in space that made the entire concept effectively illegal. A later concept, called Project Daedalus, proposed by the British Interplanetary Society in the 1970s, imagined a spacecraft powered by nuclear fusion rather than fission, igniting small pellets of fuel in a controlled chain of miniature explosions inside a magnetic engine. On paper, Daedalus could reach roughly 12% of the speed of light, fast enough to reach a nearby star system in several decades rather than tens of thousands of years. The catch, and there is always a catch, is that nuclear fusion, despite decades of research and genuine recent progress, has still never been achieved in a form compact, controllable, and efficient enough to power a spacecraft. We can trigger fusion reactions in laboratories for brief, carefully controlled moments, and we can trigger uncontrolled fusion in the form of thermonuclear weapons. But a stable, sustained fusion engine remains, even now, a technology that exists only in blueprints and simulations. A more modest and more currently achievable concept involves solar sails, enormous, ultra-thin reflective sheets that catch the pressure of sunlight itself, or the pressure of a powerful laser beamed from Earth, and use that faint but continuous push to accelerate gradually over long periods of time. A modern proposal called Breakthrough Starshot imagines launching a swarm of tiny, gram-scale spacecraft, each attached to a lightweight sail, and accelerating them, using an enormous array of ground-based lasers focused into a single powerful beam. In theory, this approach could push a tiny probe to around 20% of the speed of light within a matter of minutes of laser firing, potentially reaching Alpha Centauri in a little over 2 decades rather than tens of thousands of years. The engineering obstacles remain formidable. Building a laser array powerful enough, keeping it precisely focused on a target the size of a postage stamp across millions of kilometers, protecting a fragile sail from dust and radiation damage during a multi-decade coast through interstellar space, and figuring out how to send any meaningful data back across 4 light-years using a transmitter light enough to be carried on something the size of a smartphone chip, all remain unsolved problems, actively being researched, but nowhere near ready for an actual launch. Beyond these relatively grounded concepts lie ideas that stretch even further into speculative territory. Propulsion methods, relying on matter, antimatter, annihilation, which releases far more energy per unit of mass than any nuclear reaction, or theoretical concepts like the Bussard ramjet, which imagines scooping up interstellar hydrogen as fuel while in flight, eliminating the need to carry fuel at all. Both concepts run into serious, possibly fatal practical problems. From the near impossibility of manufacturing and storing meaningful quantities of antimatter, to calculations suggesting the drag created by scooping interstellar hydrogen might actually slow a ramjet down faster than the fuel it collects could speed it up. What all of these proposals share, from the modest and achievable to the wildly speculative, is a common thread. Every single one of them requires either energy sources, materials, or engineering precision that simply does not exist yet in any usable form anywhere on Earth. None of them are Voyager One and Voyager 2, sitting right now, decades into an actual, ongoing mission, already farther from home than anything else humans have ever built. The gap between what we have already sent and what would actually be required to reach another star system within a human lifetime is not a gap of years or even decades of additional engineering. It is a gap defined by fundamental limits in energy, materials, science, and propulsion physics that remain unsolved despite genuine, serious effort from some of the most capable engineers and physicists of the past several generations. Even if every engineering obstacle we just described were somehow solved tomorrow, even if a working fusion engine or a functioning antimatter drive suddenly became real, a deeper problem would remain, one that has nothing to do with propulsion and everything to do with being human. A human lifetime is short. Even under generous, optimistic assumptions about future medicine, it remains a handful of decades, a window that closes long before most of these journeys could ever be completed. Even the most optimistic proposals, the ones assuming fusion engines or laser-propelled sails reaching a meaningful fraction of light speed, describe journey times of decades to centuries to reach even the very nearest star system, and that is before accounting for slowing down at the destination, which, for any mission actually intending to explore or settle a new system rather than simply fly past it, roughly doubles the energy and engineering challenge all over again. This mismatch between human lifespan and interstellar distance has led to serious, sober proposals for what are usually called generation ships, enormous, self-contained vessels designed to support not the original crew who departed, but their descendants, born, raised, and eventually growing old, entirely within the confines of the ship, with only their grandchildren or great-grandchildren ever setting foot on the destination world. Such a ship would need to be, in every meaningful sense, a fully closed ecological system, recycling air, water, and waste indefinitely, growing food across dozens of generations, maintaining social and psychological stability across a population that would live, love, argue, and eventually pass away, entirely inside a metal shell, drifting through the dark, having never known any other kind of sky. The challenges here are not purely mechanical. They are social, biological, and psychological in ways that engineering alone cannot solve. Would a crew, generations removed from the people who made the original decision to leave, still share that decision's original purpose? Would cultural drift, isolation, and the simple pressures of confined, resource-limited existence eventually threaten the mission's very survival, long before the ship ever reached its destination? These are not idle questions. They are active areas of serious academic research, drawing on fields as different as closed-loop ecology, orbital mechanics, and sociology. Precisely because a journey lasting many human generations raises problems that no amount of thrust or fuel can address. Beyond the human factors lies the sheer physical hazard of the journey itself. Interstellar space is not simply empty and safe, waiting patiently to be crossed. It contains sparse but real clouds of gas and dust, along with a constant, unshielded bombardment of high-energy cosmic rays, charged particles accelerated to extraordinary speeds by distant supernovae and other violent astrophysical events. On Earth, and even in low orbit, we are shielded from most of this radiation by the planet's magnetic field and thick atmosphere. A spacecraft crossing light years of open interstellar space enjoys no such protection, and any crew aboard would face a slow, cumulative radiation exposure that current spacecraft shielding technology cannot fully solve for a journey lasting decades, let alone centuries. Even a single grain of dust, encountered at a meaningful fraction of the speed of light, carries kinetic energy comparable to a small explosive. Because kinetic energy scales with the square of velocity, meaning a speck of interstellar dust moving relative to a spacecraft at even a modest fraction of light speed can strike with the force of a far larger, slower-moving object. Any real interstellar mission would need shielding, capable of surviving thousands of years of exposure to exactly this kind of hazard, a requirement that adds mass, which, by way of the same unforgiving rocket equation we discussed earlier, adds enormous additional cost in fuel and energy. And then there is the problem of communication, the quiet, often overlooked cost of sheer distance. Even a message traveling at the absolute speed limit of the universe, the speed of light itself, takes over 4 years to reach Alpha Centauri, and over 4 more years for any reply to return. A conversation between Earth and a crew traveling toward even the nearest star system would not resemble a conversation at all. It would resemble a slow, patient exchange of letters, each one composed years before its answer arrives, a form of communication that removes any possibility of real-time guidance, real-time correction, or real-time comfort for anyone making that journey. Every layer of this problem, propulsion, energy, shielding, psychology, and communication, compounds the others, and together they explain why, despite genuinely brilliant proposals stretching back over half a century, humanity has never come remotely close to attempting an actual interstellar mission. We have only ever managed to send a handful of robotic spacecraft drifting slowly outward, on trajectories that will, given enough time, eventually leave the solar system, but that were never actually designed, equipped, or intended to reach anywhere else at all. Voyager One and Voyager Two are not alone out there, even if they are, by a wide margin, the farthest along. 2 earlier spacecraft, Pioneer 10 and Pioneer 11, launched in the early 1970s, are also on trajectories that will eventually carry them out of the solar system, moving slower than the Voyagers, having received smaller gravity assists during their own, more limited planetary flybys. Both Pioneer spacecraft went silent decades ago, their power sources exhausted long before the Voyagers, and both are now completely untrackable, their exact positions known only approximately, calculated from their last confirmed trajectory rather than any ongoing signal. They are out there, moving, following the same basic physics as the Voyagers, gradually slowing under the sun's fading pull, destined for their own multi-thousand-year crossing of the Oort cloud. But we have no way to check on them, no way to confirm their exact position, no way to know if they have struck anything or drifted subtly off course. They are, in the truest sense, lost, not in the sense of being destroyed, but in the sense of being untraceable, wandering somewhere in a volume of space too vast and too empty for us to pinpoint a single small object within it. New Horizons, launched decades later in the 21st century, after its historic flyby of Pluto and a subsequent visit to a distant, ancient object called Arrokoth, deep in the Kuiper Belt, is also headed outward on an escape trajectory. Though it launched with more advanced instruments, a longer projected operational lifetime, and a slightly different departure angle than any of the older spacecraft. Each of these missions represents the same basic story, told with slightly different numbers. A powerful initial launch, one or more gravity assists borrowed from the outer planets. A coast phase that will eventually stretch across tens of thousands of years, and an ultimate silence arriving decades before the actual departure from the solar system, followed by a journey that will continue for millennia after any human alive today has been gone for just as long. None of these spacecraft carry enough fuel, enough power, or enough speed to arrive anywhere in particular. None of them are aimed at another star system with any real precision, because precision aiming across such distances, accounting for the fact that target stars are themselves moving through the galaxy over the tens of thousands of years such a journey would require, was never a design goal any of these missions attempted to solve. They will, each of them, eventually leave the sun's gravitational domain, at some point tens of thousands of years from now, and continue drifting through the vast, mostly empty space between stars, essentially forever, since there is nothing out there to stop them, no atmosphere to burn them up, no significant matter dense enough to collide with in any statistically likely sense. Voyager One carries, bolted to its side, a golden phonograph record, containing sounds and images meant to represent humanity, greetings recorded in dozens of languages, music spanning cultures and centuries, diagrams intended to convey, to whatever might eventually find it, some sense of who built it and why. It was included not because anyone expected it to be found soon, or perhaps ever, but as a kind of message in a bottle, cast into an ocean so vast that the odds of it ever washing up on any particular shore are almost impossible to calculate meaningfully. If it is ever found, it will likely be found by something or someone entirely unrelated to any civilization currently known to exist, at a point so far in the future that the humans who built it, launched it, and celebrated its early milestones will be, to whoever encounters it, as distant and unknowable as the earliest stone toolmakers are to us. The record itself is worth describing a little more fully, because the choices made in assembling it reveal just how seriously the people behind the Voyager mission took the idea that this object might genuinely outlast every trace of human civilization here on Earth. The committee tasked with assembling its contents, led by the astronomer Carl Sagan, spent months deciding exactly what should represent an entire species and an entire planet to whatever might eventually find it. They included greetings spoken in dozens of human languages, ranging from ancient tongues no longer spoken by anyone alive to widely used modern languages, each offering a brief, warm message of welcome recorded by native speakers. They included a carefully chosen selection of music, spanning traditions from cultures across the entire globe, alongside natural sounds meant to represent Earth itself: wind, thunder, rainfall, the calls of birds and whales, footsteps, laughter, a heartbeat, an attempt to capture something of what it actually felt and sounded like to be alive on this particular planet at this particular moment in its long history. They etched a set of scientific diagrams onto the record's cover, including a map of pulsars, precisely timed cosmic lighthouses whose distinctive, predictable patterns could theoretically allow anyone or anything capable of astronomy to calculate the exact location and launch date of the spacecraft, even if every other piece of context about its origin had long since been lost. They included instructions, expressed entirely in mathematics and physics rather than any spoken language, for how the record itself should be played, since no assumption could safely be made about whether the eventual finder would have any concept of a phonograph at all. Every choice reflects the same underlying awareness we discussed earlier, that this message was never expected to be received soon, and quite possibly never expected to be received at all, yet was assembled with the same care and seriousness as if delivery were certain. That is the true scale of the journey Voyager One is on, and the true scale of what it means to actually leave a solar system. Not a headline, not a single dramatic crossing celebrated for a news cycle and then forgotten, but a slow, patient, multi-thousand-year departure that will not finish within any time frame a human mind naturally comprehends. The slow dimming of the Voyager spacecraft is, in its own way, as revealing about the scale of this problem as the physics of gravity and speed. Both spacecraft launched with 3 radioisotope thermoelectric generators each, devices that convert the heat of decaying plutonium into usable electricity through a process with no moving parts, chosen specifically because sunlight, the power source used by nearly every other spacecraft, becomes far too faint to rely on once you travel this far from the sun. Plutonium decay is steady and utterly indifferent to human schedules, releasing slightly less heat with each passing year. Following a curve dictated entirely by the isotope's physical half-life rather than anything engineers can control or accelerate. Mission controllers on Earth have spent decades managing this slow decline with remarkable care, prioritizing which instruments stay powered and which are permanently switched off, in an order chosen to preserve the most scientifically valuable measurements for as long as physically possible. The cameras on both spacecraft were shut down first, deliberately, not long after their historic photographs of the outer planets were taken. Because imaging systems draw significant power and offer little scientific value once there is nothing nearby left to photograph, only the featureless dark of open space. Heaters warming individual instruments were turned off next, one at a time, over the following decades. Even though switching off a heater risks the instrument behind it freezing permanently, becoming unusable regardless of how much power might later be available. Remarkably, several instruments that engineers expected to fail once unheated in the extreme cold of deep space have continued operating anyway, considerably outliving the temperature ranges they were originally designed and tested for. A small, unplanned bonus squeezed out of hardware built with far more margin than anyone at the time realized they were including. Even the process of communicating with the spacecraft has had to adapt. Signals from Voyager One now take over 23 hours to reach Earth, one way, meaning any command sent to the spacecraft and any confirmation that command worked involves a round trip of nearly 2 full days, an operational reality that makes even routine maintenance a slow, deliberate, patience-testing process for the small remaining team still overseeing the mission. As of the most recent estimates, engineers expect both spacecraft to lose the ability to power any scientific instrument at all, sometime in the early to mid-2030s, after which they may continue transmitting a bare, instrumentless signal for a short additional period, before falling permanently and irreversibly silent. When that silence finally comes, nothing about the spacecraft's physical situation will actually change. It will still be moving at essentially the same speed it is moving today, still following the same hyperbolic trajectory, still climbing, almost imperceptibly slowly, out of the sun's gravitational well. The silence marks the end of our ability to hear from it, not the end of its journey, which is precisely the point that makes this story so strange to sit with. The most dramatic, headline-worthy moments of the Voyager mission, the planetary flybys, the golden record, the heliopause crossing, all happened within the first several decades of a journey that will ultimately span tens of thousands of years before it reaches any kind of true conclusion. We built something, launched it, celebrated it, learned from it, and will eventually stop hearing from it entirely, all within a single human lifetime, while the object itself continues on, alone, for a length of time so much longer than the portion we witnessed that our entire involvement with it amounts to little more than the very first heartbeat of its actual existence. It helps, at this point, to widen the lens a little, because the sun is not the only object in the galaxy struggling to hold on to things, and it is not the only object that occasionally loses that struggle entirely. Astronomers have discovered, through both direct observation and theoretical modeling, that entire planets can be flung out of their home star systems, ejected permanently into interstellar space, usually through violent gravitational interactions with other planets or passing stars earlier in that system's history. These worlds are called rogue planets, and unlike Voyager One, which remains gravitationally bound to the sun for tens of thousands of years, yet a rogue planet has already crossed the finish line, already achieved true escape, drifting through the galaxy entirely untethered to any star, Its surface, if it has one, plunged into permanent, absolute darkness, warmed only by whatever internal heat remains from its own formation. Estimates for how many rogue planets exist in our galaxy alone vary enormously, from a number roughly comparable to the number of stars, to estimates suggesting there could be many times more rogue planets drifting through interstellar space than there are planets still orbiting stars at all. If those higher estimates hold up, it would mean that being gravitationally bound to a star, the way every planet in our own solar system currently is, might actually be the less common outcome across the galaxy as a whole, and that permanent, achieved escape, the very thing this entire story has been circling around, might be closer to the galactic norm than the exception. Stars themselves are not immune to this either. In rare, extreme circumstances, a star can be ejected from its own galaxy entirely, accelerated to speeds high enough to escape the combined gravity of hundreds of billions of stars, usually through an encounter with a supermassive black hole at a galaxy's center, which can, under the right conditions, act like an enormous gravitational slingshot, flinging one member of a stellar pair outward at extraordinary velocity while capturing its former companion permanently into a tight orbit. These are called hypervelocity stars, and several have actually been identified, moving fast enough that they will, given enough time, leave the Milky Way entirely, sailing out into the vast emptiness between galaxies, never to return, their light fading from any observer left behind, long before they reach any other galaxy to call home. Set against that backdrop, the story of Voyager One starts to look less like a unique curiosity and more like a small, human-scale example of a pattern that plays out across the entire universe, on every scale, from spacecraft to planets to stars, the same basic physics of gravity and escape velocity governing all of it. The same fundamental question: is your total energy positive or negative? Deciding whether something is bound forever or free forever, applying just as much to a 500-kilogram spacecraft as it does to a star many times more massive than our own sun. The difference, and it is a significant one, is scale. A rogue planet or a hypervelocity star has already, definitively, completed its escape, having been given, through violent, one-time gravitational encounters, speeds far beyond anything a gentle series of planetary flybys could ever provide. Voyager 1 received a comparatively gentle nudge, just barely enough to guarantee eventual escape, but nowhere near enough to make that escape quick. It is less like the dramatic ejection of a rogue planet, and more like a very, very slow release. A decades-long unclenching of a gravitational fist that will not fully open for tens of thousands of years yet. A difference not of kind, but of degree, the same physics playing out at a dramatically gentler, dramatically slower pace. The boundary of the solar system is not a one-way barrier either, and this is where the story becomes genuinely strange, because if objects can eventually leave, given enough speed and enough time, then objects from other star systems can, in principle, arrive. For most of the history of astronomy, this remained a purely theoretical possibility, discussed in textbooks but never actually observed, until a night in the fall of 2017, when a telescope in Hawaii detected something moving through the inner solar system on a trajectory unlike anything ever recorded before. Its path was hyperbolic, the same term we used earlier to describe Voyager 1's own escape trajectory, except this object was moving the opposite direction, inbound, having arrived from somewhere among the stars, swung once around the sun under the pull of its gravity, and was already on its way back out, never to return. It was given the name Oumuamua, a word drawn from Hawaiian meaning something like a scout or messenger sent from the distant past, and its discovery confirmed, for the first time in recorded history, that our solar system is not a sealed container, but a system with a permeable edge, one that other star systems' debris can, on rare occasions, wander into and back out of again. Oumuamua was strange even by the standards of a genuinely unprecedented discovery, its shape apparently elongated far beyond anything typical of solar system comets or asteroids, its brightness varying in ways that suggested a tumbling, cigar-shaped or pancake-shaped body, and its trajectory showing a subtle, unexplained acceleration as it departed, a detail that sparked years of scientific debate over whether that acceleration came from ordinary outgassing, the same process that pushes comets slightly off their expected paths, or something else entirely. Most astronomers ultimately settled on outgassing, likely from frozen hydrogen or nitrogen ice, sublimating in ways too faint to detect directly but sufficient to nudge the object's path, though the debate itself illustrated just how little we actually know about objects that spend most of their existence drifting through the truly empty space between stars, arriving at our solar system as complete strangers, carrying no history we have any way of reading. 2 years later, in 2019, a second interstellar visitor was confirmed. This one discovered by an amateur astronomer and given the name Borisov, and unlike Oumuamua's ambiguous, asteroid-like appearance, Borisov behaved unmistakably like a comet, complete with a visible tail of gas and dust, offering astronomers a far clearer look at what material from another star system's own Oort cloud, flung outward by its own gravitational encounters, actually looks like up close. Both objects followed the exact same physics we have spent this entire story describing, just running in reverse. They arrived with enough speed, enough positive total energy relative to the Sun, that they were never going to be captured into any kind of orbit, curving briefly through our solar system's inner regions before continuing on their way back out into interstellar space, following hyperbolic paths that will carry them eventually toward some other star system entirely, or perhaps toward none at all, doomed to drift alone between galaxies' worth of stars for the remainder of their existence. This detail matters enormously to the larger question this story has been asking, because it confirms, through direct observation rather than theory alone, that the Oort cloud, and objects like it, are not unique to our own Sun. Other stars almost certainly have their own version of this same icy, sparse, distant shell of debris, their own slow, gravitationally bound populations of comets, occasionally stirred loose by a passing star, sent wandering across the galaxy for millions of years, until, on rare occasions, one happens to pass close enough to another star system to be noticed, studied, and named, before continuing on its own multi-million-year journey through the dark. Given how rare these detections have been, spotted only twice in the entire history of astronomy, despite the fact that such objects are almost certainly passing through constantly, largely too small and too faint to notice, it stands to reason that our own solar system's Oort cloud has been sending its own icy messengers outward for billions of years, unnoticed, unnamed, and unrecorded, arriving at other stars entirely unannounced, carrying no trace of who sent them or why. This brings us back to the question we opened with, the confusion sparked by that 2012 announcement, and it is worth untangling exactly what happened, because the confusion was not entirely the public's fault. Even within the scientific community, there was genuine, published disagreement about how to describe what Voyager One had actually done, a disagreement that played out in academic papers and press releases over the following years, rather than being settled cleanly in a single afternoon. Some scientists argued that crossing the heliopause, leaving the direct influence of the solar wind, was the most meaningful and detectable boundary available, the clearest, most measurable line a spacecraft could actually cross, and that calling this moment the departure from the solar system was reasonable, given that no spacecraft would live anywhere near long enough to reach the far more distant, far more gradual boundary of the Oort cloud. Other scientists pushed back firmly, arguing that defining the solar system by the reach of the solar wind ignored gravity entirely, and that a definition based on gravitational dominance, the region where the sun remains the primary force governing an object's motion, was the only physically rigorous way to describe the true edge of what belongs to our star. NASA itself, in the years since, has generally tried to hold both ideas in view at once, describing the heliopause crossing as Voyager One entering interstellar space, a specific, well-defined, and genuinely historic achievement, while being careful, in more detailed explanations, to note that this is distinct from actually leaving the sun's gravitational influence, which remains tens of thousands of years away. The distinction matters because interstellar space and outside the solar system are not, strictly speaking, describing the exact same thing, even though the phrases sound almost interchangeable in ordinary conversation. Interstellar space refers to the material that fills the space between stars, the thin plasma, dust, and cosmic rays that exist independently of any particular star's influence. And Voyager 1 is now measurably surrounded by that material, having left the plasma bubble the sun blows around itself. Being gravitationally bound to the sun and being surrounded by interstellar material are not contradictory states. An object can be both at once, immersed in the same thin material that fills the space between every star in the galaxy, while still being held, faintly but genuinely, in a long, slow orbit around our own particular star. This is, in a strange way, similar to how someone can step outside the walls of a house and still be standing on that house's property, still within its yard, still subject to whatever rules and boundaries apply there, even though they have clearly left the building itself behind. Voyager 1 left the building. It has not yet left the yard, and the yard, in this analogy, happens to be almost unimaginably larger than the building ever was. Understanding this distinction does not diminish what Voyager 1 accomplished in 2012. It remains the first spacecraft in history to measure, directly and unambiguously, the properties of the material that fills interstellar space, providing scientists with real data about a region previously known only through indirect observation and theoretical modeling. A genuine, permanent contribution to human knowledge that no later mission can ever repeat for the first time again. But it does mean that the popular framing, the idea that Voyager 1 left the solar system entirely in 2012, oversimplified a far stranger, far slower, and ultimately far more interesting story. One where the true departure is not a single dramatic crossing, but a gradual, multi-thousand-year unwinding of a gravitational bond that no spacecraft humanity has ever built or is likely to build for a very long time, will actually live to see completed. The outer solar system holds one more mystery worth mentioning here, because it touches directly on this same question of what actually governs motion at extreme distance from the sun, and it remains, as of now, genuinely unresolved. Over the past couple of decades, astronomers surveying the most distant known objects in the solar system, icy bodies orbiting even farther out than Pluto, I noticed something odd in the way several of these objects were arranged. Their orbits, rather than being randomly scattered in every direction, the way you might expect from bodies flung outward by chaotic gravitational encounters with the giant planets long ago, appeared instead to cluster together, aligned in a way that seems statistically unlikely to occur by chance alone. Two astronomers proposed an explanation in 2016 that captured public imagination almost immediately, suggesting that the clustering could be explained by the gravitational influence of an undiscovered ninth planet, several times the mass of Earth, orbiting far beyond even these already extremely distant objects, its gravity subtly herding their orbits into the alignment observed. This hypothetical world, generally referred to simply as Planet 9, would, if it exists, orbit at a distance so extreme that even Neptune's own orbit would look modest by comparison, taking somewhere on the order of 10 to 20,000 years to complete a single full circuit around the Sun. No telescope has directly confirmed its existence. The evidence remains entirely indirect, based on the gravitational fingerprints it would leave on smaller, closer objects, rather than any direct detection of the planet itself. And several alternative explanations have been proposed over the years, including the possibility that the clustering is a selection effect caused by where and how astronomers happen to search the sky, rather than genuine evidence of an unseen world. The debate remains active and unresolved, with dedicated searches ongoing, using some of the most powerful survey telescopes available, specifically designed to scan wide swaths of sky for the faint, slow-moving signature such a distant world would produce. What makes this relevant to our larger story is the reminder it offers that even within the region we might casually think of as fully mapped and understood, the outer solar system remains full of genuine, active mystery, populated by objects and possibly entire undiscovered planets whose gravity still shapes the architecture of everything out there, including, potentially, the exact structure and behavior of the Oort cloud that any future spacecraft or any future comet drifting toward the inner solar system will eventually have to pass through or interact with. If Planet 9 exists, its gravity would represent yet another factor complicating the clean, simple picture of a spacecraft sailing steadily outward under the Sun's gentle, weakening pull alone. Any object passing through its vicinity, at the extreme distances where its influence would matter most, could have its trajectory subtly altered, nudged one way or another by a source of gravity we have not yet even confirmed is real. A reminder that our map of the solar system's outer reaches, however detailed it has become, remains genuinely incomplete, still being filled in, piece by piece, by ongoing observation rather than settled, finished knowledge. Knowing everything we now know about how slow this journey actually is, it is fair to ask whether a dedicated mission, built specifically and only to escape as quickly as possible, could do meaningfully better than the Voyagers managed, almost by accident, as a side effect of a grand tour designed primarily to photograph planets. The answer is yes, to a point, and mission planners have spent years designing exactly this kind of concept, generally referred to as an interstellar probe, intended not to visit any particular planet, but simply to travel outward, fast, carrying instruments capable of studying the heliopause, the interstellar medium beyond it, and the inner edge of the Oort cloud in far greater detail than either Voyager was ever designed to provide. The proposed approach typically involves launching on the most powerful rocket available, skipping the kind of slow, multi-planet gravity assist tour the Voyagers used, and instead flying directly and quickly toward Jupiter, using a single close pass for a strong initial boost. Some more ambitious versions of the concept go a step further, proposing a maneuver that sends the spacecraft diving in close to the Sun first, deliberately entering a much deeper part of the Sun's gravity well, before firing its engines at the point of closest approach, taking full advantage of the Oberth effect we described earlier, when the benefit of firing an engine is dramatically multiplied by already moving at extremely high speed. Combined together, a close solar pass, a powerful engine burn timed precisely at that moment, and a subsequent gravity assist from Jupiter could, according to detailed mission studies, produce a spacecraft moving considerably faster than either Voyager ever achieved, potentially reaching speeds in the range of double what Voyager One currently manages, or more. Even with that improvement, the honest numbers remain sobering. A spacecraft launched with this kind of aggressive trajectory design might reach the same distance it took Voyager 1 nearly 5 decades to reach in only around half that time, and might cross into the inner edge of the Oort cloud within roughly a century or two of launch, rather than the several centuries Voyager 1 will require. That is a genuine, meaningful improvement, one worth pursuing, and serious engineering studies for exactly this kind of mission have been conducted repeatedly over the past several decades, occasionally gaining real institutional support and funding for detailed design work. But having or even quartering the time required to reach the inner Oort cloud does very little to solve the deeper problem. Because crossing the inner edge is not the same as completing the crossing. Even a spacecraft, moving twice as fast as Voyager 1, would still require somewhere in the range of 10 to 15,000 years to cross the entire breadth of the Oort cloud and reach the true outer boundary of the Sun's gravitational dominance. Faster, in other words, helps, but it does not fundamentally change the category of problem we are dealing with. It shortens a journey measured in tens of thousands of years, down to a journey still measured in many thousands of years. An improvement real enough to matter for scientific purposes, allowing instruments to gather data from farther out sooner, but nowhere near enough to bring the true edge of the solar system within reach of any human institution, government, or civilization that we can currently guarantee will still exist by the time such a journey concludes. This is, in the end, the honest shape of the problem this story keeps circling back to, over and over, from every possible angle: propulsion, gravity, time, and distance. Escaping the sun's gravity in the strict, technical sense, achieving a trajectory with positive total energy, is something we have already done 4 separate times, with 4 separate spacecraft, using nothing more advanced than careful trajectory planning and a fortunate alignment of planets. Actually leaving, in the complete, physical sense of clearing the entire volume the sun still gravitationally dominates, is something that remains, and will remain for the foreseeable future, entirely beyond the reach of anything humanity has ever built or seriously proposed building. There is a particular kind of vertigo that comes from trying to hold a timescale like this in your mind, honestly, rather than simply letting the number wash past as an abstraction. Tens of thousands of years is not a length of time humans evolved to intuitively grasp. Our sense of time, shaped by seasons, lifespans, and the rhythms of a single spinning planet, tops out somewhere around a single human lifetime, extends a little further through the memory of grandparents and the stories they pass down, and beyond that, becomes almost entirely abstract, a number on a page rather than a felt, lived reality. Geologists have their own tools for coping with this problem, ways of translating deep time into something closer to human scale, and one of them is worth borrowing here. If you compress the entire span of time, Voyager 1 needs to complete its journey through the Oort cloud into a single ordinary year, with the spacecraft's departure from the heliopause in 2012 marking the first moment of January. Then by the time you reached February, the entire history of written language, every book, every letter, every recorded word in human history, would not yet have been invented. Agriculture, cities, and the earliest permanent human settlements would not appear until sometime around March. The pyramids of Egypt would not be built until early April. Every empire, every war, every scientific discovery, every piece of art created by every civilization in recorded human history would need to fit somewhere between April and the final days of December, an entire compressed span of roughly 10,000 years of actual civilization crammed into the last 3/4 of that single calendar year. With the spacecraft's actual, final departure from the solar system's gravitational grip not arriving until sometime the following January, a full year after it first crossed the heliopause, on the same compressed scale. This is, in effect, what it means to say the Oort cloud crossing takes 30,000 years. It is not simply a large number. It is a span of time roughly 3 times longer than the entire history of human civilization, as most historians define it, stretched out ahead of a spacecraft that, on the scale of that same journey, has barely left the driveway. Even Earth itself, over that same span of time, will not remain entirely unchanged. Continents drift at a pace of a few centimeters each year, barely perceptible within a single lifetime, but compounding steadily over tens of thousands of years into measurable, mappable shifts. Coastlines reshape as ice ages advance and retreat on their own multi-thousand-year cycles, driven by slow, predictable wobbles in the tilt and orbit of the planet itself. By the time Voyager One completes its crossing of the Oort cloud, assuming it survives that long, undamaged by any stray collision with dust or debris across such an enormous span of time, the Earth it departed from will likely look different in ways subtle enough to go unnoticed year to year, but significant enough, over the full span of the journey, to reshape coastlines, shift the exact pattern of ice at the poles, and quite possibly render obsolete every map any human alive today has ever studied. This is the true weight behind the phrase impossible to escape the solar system. It is not impossible in the sense of violating physics. The physics, as we have seen, already permits it, already guarantees it, for any object moving fast enough to achieve positive total energy relative to the Sun. It is impossible in the sense that matters far more to us, practically, as short-lived, impatient creatures who evolved to care about tomorrow, next season, and at most the well-being of our own grandchildren. It is impossible on any timescale a human civilization, a human institution, or a single human life could ever hope to witness completed from beginning to end. Astronomers have actually calculated, using known stellar positions and velocities, roughly what Voyager One and Voyager Two will experience, long after their instruments and transmitters have gone silent, tracing their projected paths forward across the galaxy for tens of thousands of years, using nothing more than basic orbital mechanics and the best available data on how nearby stars are moving. In roughly 40,000 years, Voyager One is projected to pass within a couple of light-years of a small, faint star, currently cataloged simply by a string of letters and numbers. Sitting in the constellation Camelopardalis, a star far too dim to have earned any common name, one that will, at the moment of that distant flyby, briefly become the nearest star to a piece of human-made hardware. Even though the spacecraft will not be traveling toward it in any intentional sense, simply passing near it by the ordinary, indifferent mathematics of two independent trajectories happening to intersect in the same rough region of space at the same rough moment. Voyager 2, on a slightly different heading, is projected to pass somewhat close to a star called Ross 248 in a similar time frame, and considerably further out, within the next few 100,000 years, both spacecraft will have drifted past several other stars at varying, generally enormous distances, none of them close enough for any kind of meaningful gravitational interaction, none of them close enough to alter the spacecraft's course in any noticeable way. These flybys are not visits in any meaningful sense of the word. At the distances involved, several light-years in most cases, a star's gravity is far too weak to bend a spacecraft's path significantly, meaning Voyager 1 and Voyager 2 will simply continue along their existing hyperbolic trajectories relative to the Sun, largely undisturbed, for the entire remainder of these calculations, which stretch, in some published studies, out to 1,000,000 years or more into the future. 1,000,000 years is a span of time so far beyond ordinary human comprehension that even the deep time comparisons used earlier in this story start to lose their usefulness. A span roughly comparable to the entire time modern humans and our immediate evolutionary ancestors have existed as a recognizable lineage, stretched out again, entirely ahead of a spacecraft that will, throughout all of it, remain nothing more than a small, cold, silent piece of metal tumbling gently through the vast, mostly empty space between stars. Nothing about this future is dramatic. There is no final destination written into Voyager One's trajectory. No star it is aimed at. No moment of arrival anyone has planned for or expects. It will simply continue, indefinitely, following the same basic physics that carried it this far, gradually leaving the Sun's gravitational influence behind over the next tens of thousands of years. Then, continuing to drift through the wider galaxy for a length of time that, as far as current models suggest, has no natural endpoint at all, other than the extremely remote, essentially negligible chance of an eventual collision with some other object, sometime across a span of time so long that the Sun itself will have changed dramatically before it ever happens, swelling in its final stages into a much larger, much brighter star. Long after Earth itself has ceased to be hospitable to anything resembling the civilization that built the spacecraft in the first place. There is one more layer to this problem worth addressing directly, because it is the question people often reach for once they have absorbed everything else. The question of whether some future breakthrough in physics itself, rather than merely engineering, might eventually change the equation entirely. Einstein's theory of special relativity places a firm, well-tested limit on how fast anything with mass can travel through ordinary space. A limit set by the speed of light itself, which no object carrying mass can ever reach, let alone exceed, no matter how much energy is poured into accelerating it. As an object's speed approaches the speed of light, the energy required to add each additional small increment of velocity grows without bound, approaching infinity as the object's speed approaches light speed itself, meaning that reaching light speed exactly would require an infinite amount of energy, a threshold that makes exceeding it through conventional acceleration mathematically impossible rather than merely difficult. This is not a limitation of current engineering, the way the rocket equation's fuel problem is. It is a fundamental property of space and time themselves, confirmed through more than a century of rigorous experimental testing, from particle accelerators pushing subatomic particles to enormous fractions of light speed, to precise measurements of time dilation aboard high-speed aircraft and orbiting satellites, all consistently matching the predictions of relativity to extraordinary precision. This is where more speculative, genuinely theoretical proposals enter the conversation. Ideas that attempt to sidestep the speed limit not by moving faster than light through space, but by manipulating space itself. The most famous of these is a concept called the Alcubierre drive, proposed by a physicist in the 1990s, which describes a mathematically valid, if wildly impractical, solution to the equations of general relativity, involving a bubble of contracted space ahead of a spacecraft and expanded space behind it, effectively allowing the bubble itself to move faster than light relative to the wider universe, while the spacecraft inside the bubble remains stationary relative to the bubble's own local space. On paper, in the pure mathematics, this does not violate relativity, because the spacecraft never actually exceeds the speed of light within its own local region of space. It is the space itself being warped that does the traveling. In every practical sense, however, the Alcubierre drive remains firmly in the realm of theoretical curiosity rather than genuine engineering possibility. The energy requirements calculated for even a modest version of such a bubble, sized for a small spacecraft, have historically come out to values vastly exceeding the total energy output of every star in the observable universe combined, though later refinements to the concept have managed to reduce that requirement dramatically, still leaving it, by every current estimate, far beyond anything achievable with any material or energy source currently known to exist. The proposal also requires a form of matter with negative energy density, a theoretical substance that has never been observed or confirmed to exist in the quantities or configuration such a drive would require, meaning the entire concept rests on a foundation that remains, honestly, unconfirmed physics layered on top of unconfirmed engineering. None of this means such ideas are worthless. Genuine, serious physicists continue to study and refine these proposals, not because a working warp drive is expected anytime soon, but because working through the mathematics of extreme, exotic scenarios often reveals deeper truths about the underlying structure of space and time itself. Insights that have, historically, occasionally led to genuinely useful discoveries in entirely unrelated areas of physics. But as things stand today, and as they are likely to stand for a very long time to come, nothing in physics offers a genuine shortcut around the problem this entire story has described. Chemical rockets cannot reach interstellar speeds because of the unforgiving mathematics of the rocket equation. Nuclear and fusion propulsion remain theoretically promising but practically unrealized, decades of research away from a working engine. Laser-propelled sails remain the most currently plausible path to a meaningful fraction of light speed, but only for objects small enough to fit in the palm of a hand, offering no realistic path for carrying a human crew or even a full-sized robotic probe with a real communications array. And true faster-than-light travel, the only approach that could realistically bring another star system within reach of a single human lifetime, remains, as far as every confirmed law of physics currently allows, simply and firmly off the table. It is worth stepping back for a moment and asking not whether escaping the solar system quickly is possible with our current technology, which we have already established it is not, but whether it might become possible for some future version of human civilization, given enough time, enough accumulated knowledge, and enough available energy. Scientists sometimes use a rough framework called the Kardashev scale to think about this kind of question, a way of categorizing hypothetical civilizations not by their culture or their achievements, but simply by how much energy they are capable of harnessing and using. A civilization capable of harnessing all the energy available on its home planet, capturing and directing the full energy budget of its atmosphere, oceans, and geological processes, is sometimes described as a Type 1 civilization, a threshold humanity has not yet fully reached, though we are, by some estimates, a meaningful fraction of the way there. A civilization capable of harnessing the full energy output of its entire home star, potentially through a theoretical structure called a Dyson swarm. A vast collection of solar collectors surrounding a star and capturing a significant fraction of its total light output is described as a Type 2 civilization, a level of energy command that remains, for now, entirely speculative, existing only in physics, papers, and science fiction. At that level of available energy, the kind of propulsion systems that currently exist only as blueprints and thought experiments, sustained fusion drives, large-scale antimatter production, even the exotic negative energy requirements of a theoretical warp bubble, start to look, for the first time, like problems of engineering scale rather than problems of fundamental physical impossibility. A civilization with access to a meaningful fraction of an entire star's energy output could, in principle, afford propulsion systems requiring energy budgets that would currently sound like obvious fantasy, the kind of numbers that make a Project Daedalus-style fusion drive look modest and achievable by comparison. Humanity, right now, sits nowhere near that threshold. Our entire civilization's current energy consumption, from every power plant, every engine, every device on the planet combined, remains an almost vanishingly small fraction of even the energy the sun deposits on Earth's surface every single day, let alone the sun's total energy output radiating in every direction across the solar system. This framing offers a useful, honest way to understand the true scale of the interstellar travel problem, separate from any question of clever engineering or bold ambition. It is not primarily a problem of insufficient imagination, and it is not primarily a problem of insufficient scientific understanding, since the physics involved, relativity, rocket dynamics, gravitational mechanics, has been well understood, in broad outline, for well over a century. It is, fundamentally, a problem of energy, and more specifically, a problem of the sheer, staggering gulf between the energy budget available to a civilization still confined almost entirely to a single planet, and the energy budget that any realistic interstellar mission, whether crewed or robotic, would actually require to make a meaningful crossing within any time frame shorter than tens of thousands of years. Closing that gulf is not obviously impossible in any permanent, physics-violating sense, the way faster-than-light travel through ordinary space appears to be. It may simply be a problem of time, the kind of problem that a civilization several centuries or millennia more advanced than our own, having fully harnessed the energy resources of its own solar system, might approach with tools and technologies that would look, to us, as unrecognizable and implausible as a smartphone would have looked to someone living before electricity was first harnessed and understood. Whether humanity ever reaches that point, whether our civilization survives, advances, and accumulates that level of energy command across the many centuries such progress would likely require, remains an open question, one this story cannot answer, and one that depends on choices, priorities, and challenges that have very little to do with rocket science at all. Given everything we have covered, the fuel that cannot be carried, the speed that cannot be reached, the decades of silence that will precede the actual departure by tens of thousands of years, it is fair to ask why any of this was worth attempting in the first place. Why launch a spacecraft on a journey it can never finish being witnessed, built by people who knew, from the very beginning, that no human alive at the time of launch, and no human alive for hundreds of generations afterward, would ever see it reach the boundary it was technically aimed at? The honest answer has very little to do with practicality, and everything to do with a much older, much more human impulse, the same impulse that sent early sailors past the horizon without knowing what, if anything, lay beyond it. The same impulse that carried explorers across unmapped mountain ranges and deserts, not because success was guaranteed, but because the not knowing itself had become unbearable. Voyager 1 and Voyager 2 were never seriously expected to arrive anywhere. Their scientific value was always going to be concentrated almost entirely in the first decade or two of their journey. The planetary flybys, the close-up photographs of worlds no human eye had ever seen in detail before, the direct measurements of magnetic fields, radiation, and atmospheric composition that transformed our understanding of the outer solar system almost overnight. Everything after that, the long, slow coast toward the heliopause, the crossing itself, and the tens of thousands of years that will follow, was always going to be an afterthought scientifically. A bonus data stream trickling in for as long as the plutonium held out, rather than the mission's primary justification. And yet the golden record was still included. The greetings in dozens of languages were still recorded, The diagrams explaining our location in the galaxy were still carefully etched into that gold-plated disk. The music spanning cultures and centuries was still selected and pressed into its grooves. All of it added not because anyone genuinely expected it to be found, but because the act of reaching outward, of trying, of leaving some trace of ourselves aimed at the dark, seemed to matter on its own terms, independent of whether anyone or anything would ever actually receive the message. There is something worth sitting with in that choice. A choice made by people who understood the odds better than almost anyone, who ran the calculations themselves, who knew exactly how vast the distances involved actually were, and who decided to include a message anyway. It suggests that the value of reaching outward was never really about the destination at all, not in any strict, arrival-focused sense. It was about the reaching itself, about the decision to build something, launch it, and let it go, fully aware that its true, complete journey would unfold across a length of time. No one involved in building it would live to see even the smallest further fraction of. This is, in a way, the same impulse behind every telescope pointed at a galaxy so far away that its light left home before the dinosaurs went extinct. The same impulse behind every mission sent to a distant moon or asteroid with no expectation of return. The same impulse that drives careful, patient scientists to spend entire careers studying processes that will not reach their conclusion within any human lifetime, satisfied instead with adding one small, honest piece to a picture that will only ever be completed by people not yet born. Voyager One is not going to escape the solar system while anyone currently alive is watching. It is not going to reach another star system, ever, in any meaningful sense of the word reach. But it is, right now, at this very moment, farther from home than anything else our species has ever built, moving steadily outward, carrying a small, careful message about who we were, on a trajectory that guarantees it will keep moving long after everything and everyone who built it has been gone for a length of time even longer than the journey itself. As it happens, this is not purely a hypothetical conversation anymore. The concept of a dedicated interstellar probe, the kind we described earlier, using a close solar pass and a Jupiter gravity assist to achieve a significantly faster departure than either Voyager managed, has moved beyond early sketches and into serious, funded engineering study, backed by teams that have spent years refining exactly how such a mission could be built using realistic, near-term technology rather than speculative future breakthroughs. The most recent Planetary Science Decadal Survey, the periodic report compiled by the scientific community to help guide which missions deserve the highest priority for funding over the following 10 years, included strong, explicit support for pursuing exactly this kind of mission, recognizing the unique scientific value of studying the heliopause and the interstellar medium directly, with instruments purpose-built for the task, rather than instruments originally designed decades earlier for planetary flybys. If such a mission does eventually launch, likely sometime in the coming decades, it would represent the first spacecraft in history built from the very beginning with the explicit, primary goal of reaching interstellar space as efficiently as possible, rather than achieving that milestone as an incidental byproduct of a mission designed for an entirely different purpose. It would carry modern instruments, capable of measuring the interstellar medium with a level of precision and detail that Voyager One's nearly 5-decade-old sensors, remarkable as they have been, simply cannot match. It would likely reach the heliopause considerably faster than Voyager One did, potentially within a couple of decades of launch rather than 3.5. Thanks to the more aggressive trajectory design made possible by modern rockets and more precise trajectory planning. And yet, even this dedicated, purpose-built mission, representing the very best that current and near-future engineering can offer, would still face the exact same fundamental limit we have spent this entire story describing. It would still take centuries, at best, to reach even the inner edge of the Oort cloud. It would still take many thousands of years to cross that cloud entirely. It would still, ultimately, fall silent decades after launch, its power source exhausted long before any team of engineers could hope to guide it through even a small fraction of the journey still required to reach the true, complete boundary of the sun's gravitational influence. This is, in its own way, the clearest possible illustration of everything we have discussed, because it represents the absolute best-case scenario available to current human engineering, the fastest, most carefully optimized departure imaginable using real, achievable technology rather than speculative fusion drives or theoretical warp bubbles. And even that best-case scenario, funded, studied, and genuinely likely to happen within our lifetimes, does not come close to solving the underlying problem. It does not bring the true edge of the solar system within reach of any single human life, any single human institution, or any civilization we can currently guarantee will still exist by the time such a journey would actually conclude. It simply moves the goalposts a little closer, shaving a few centuries off an already almost incomprehensible span of time. A genuine, worthwhile scientific achievement in its own right, but not, by any honest measure, an actual solution to the deeper question this story keeps returning to. So, let's bring this back to where it started, to that quiet contradiction sitting at the center of everything we have covered. Voyager One left the sun's protective bubble of solar wind in 2012, becoming the first human-made object to touch the material that fills the space between stars. A genuine, historic, well-earned milestone that deserves every bit of attention it received. But it did not, in that moment, leave the solar system, not in the fuller, more complete sense that gravity, rather than plasma physics, actually defines. It remains, right now, as you listen to this, still falling under the sun's pull, still tracing a slow, patient, mathematically guaranteed path toward eventual freedom, a path that will not actually complete for tens of thousands of years yet, long after its instruments have gone dark, long after the last team of engineers monitoring its faint signal has retired, long after the very idea of the Voyager mission has drifted from living memory into the realm of distant historical record. This is not a story about failure. Every calculation, every gravity assist, every carefully rationed watt of power squeezed from a slowly decaying lump of plutonium worked exactly as intended. Voyager One is on precisely the trajectory it needs to be on to eventually, genuinely, completely leave the sun's gravitational domain, a trajectory secured decades ago through careful engineering and a fortunate alignment of planets that will not repeat again for well over a century. The spacecraft is not stuck, is not failing, is not falling short of its goal in any meaningful sense. It is simply doing exactly what the laws of physics require, at exactly the pace those laws allow. Given the modest, human-scale amount of energy we were able to provide it back in 1977. What this story reveals, more than anything else, is the sheer scale of the gap between what feels close and what actually is close. A gap that becomes almost impossible to appreciate honestly until you sit with the real numbers, the real distances, the real, patient mathematics of gravity and escape. The solar system is not a tidy, walled garden with the planets scattered near its center and a clean, simple boundary marking its edge somewhere just past Neptune or Pluto. It is a vast, mostly empty gravitational domain, stretching for roughly 2 light-years in every direction from the sun, filled almost entirely with icy, scattered debris too faint and too sparse for any telescope to have ever directly seen, a domain so large that even our fastest, farthest traveling spacecraft, after nearly 5 decades of continuous outward motion, has covered only the smallest, most negligible fraction of the total distance it will eventually need to travel. We have, as a species, already accomplished something remarkable, building 4 separate spacecraft capable of achieving genuine, mathematically confirmed escape from the sun's gravity, using nothing more advanced than chemical rockets and a careful, patient understanding of orbital mechanics. That achievement stands entirely on its own, regardless of how long the full journey ultimately takes to complete. But the honest answer to the question this story asked at the very beginning, why it is impossible to escape the solar system, is not that escape itself is impossible. The physics guarantees escape, eventually, for any object moving fast enough to achieve positive total energy relative to the Sun, exactly as Voyager 1, Voyager 2, Pioneer 10, and Pioneer 11 have all already done. What is impossible, at least for now, at least with the technology and the energy resources currently available to us, is escaping quickly, escaping within any time frame a human institution could plan for, fund, and actually witness reach its conclusion. The sun does not let go easily. Its gravity, weak as it becomes at extreme distance, never actually reaches zero, reaching outward for roughly 2 light-years before finally, gradually, losing its grip to the combined pull of neighboring stars and the wider gravity of the galaxy itself. Crossing that entire distance, even at the considerable speeds our best spacecraft have achieved, takes longer than the entire span of human civilization, several times over. A length of time so vast that the 4 spacecraft currently making that journey will spend the overwhelming majority of it silent, dark, and utterly alone, carrying nothing forward but momentum, and, in Voyager 1's case, a small golden record containing everything we thought was worth saying to whoever or whatever might one day find it. That is the true shape of leaving home, when home is an entire solar system, and the door out is measured not in kilometers or years, but in the slow, patient turning of tens of thousands of years, one quiet, unwitnessed moment at a time. It is worth remembering, too, that our sense of where the solar system actually ends has never stayed still for very long, and understanding how dramatically that boundary has moved, at least in our own minds, over the past few centuries, helps explain why the confusion around Voyager 1's crossing was almost inevitable. For most of recorded history, the known solar system ended at whatever planet happened to be the farthest one visible to the naked eye. Saturn held that title for thousands of years, its faint, slow-moving point of light marking, as far as any ancient astronomer could tell, the outer edge of everything that existed. That boundary held firm until the invention of the telescope, when, in the closing years of the 18th century, an astronomer working from his own backyard observatory noticed a faint, slowly moving object that turned out to be an entirely new planet. One that immediately doubled the previously assumed size of the known solar system overnight. That planet was Uranus, and its discovery was followed, a few decades later, by the discovery of Neptune, found not by accident, but through careful mathematical prediction. Astronomers having noticed that Uranus's orbit was being subtly tugged by the gravity of some unseen, more distant world, and calculating almost exactly where that world would need to be before anyone actually pointed a telescope at it and found it waiting there. Each of these discoveries pushed the assumed edge of the solar system dramatically outward, and each time, for a while, the newly discovered planet was treated, understandably, as the true final boundary, the last object out there, before the next discovery inevitably proved that assumption wrong all over again. Pluto's discovery in the early 20th century continued this same pattern, extending the known boundary even further. And for decades afterward, Pluto held the honorary, if ultimately temporary, title of the outermost known body in the solar system. It was not until the closing years of the 20th century and the opening years of the 21st that astronomers began discovering an entire population of icy bodies similar to Pluto, scattered across a broad, disc-shaped region beyond Neptune's orbit. A region we now call the Kuiper Belt, which revealed that Pluto was never the lonely outermost sentinel it had long been assumed to be, but simply one of many similar worlds occupying a previously unmapped and unsuspected region of space. This discovery, more than any single event before it, forced a fundamental rethinking of what the outer solar system actually contained, and directly led to the extended, ongoing debate over Pluto's planetary status that still occasionally flares up in public conversation even now. And even the Kuiper Belt, vast as it is, turned out to be only a relatively nearby foothill compared to the far larger, far more distant Oort cloud, a region whose existence was proposed on purely theoretical grounds decades before any Kuiper Belt object had even been found. Based entirely on the strange, long looping orbits of certain rare comets that seemed to be arriving from some vastly more distant reservoir than anything else known at the time. Each expansion of our understanding, from Saturn to Uranus to Neptune to Pluto to the Kuiper Belt to the theorized Oort cloud, followed the exact same basic pattern, a confident sense that we had finally mapped the true edge of our own solar system, followed, sometimes within a single generation, by the discovery that the edge was actually dramatically farther out than anyone had previously realized. There is no strong reason to assume this pattern has finally, permanently stopped. The Planet 9 hypothesis we discussed earlier represents exactly this same kind of open question, an unconfirmed possibility that, if resolved one way, could once again meaningfully redraw our working picture of what actually populates the solar system's most distant reaches. Given this long, repeating history, the confusion surrounding Voyager 1's 2012 crossing looks a little less like a simple communication failure, and a little more like the latest chapter in a very old, very human pattern, one where each generation, upon finally reaching what feels like the edge of everything, discovers that the true edge was always sitting quietly, patiently, considerably farther out than anyone standing at that particular moment in history had any real way of knowing. There is a strange comfort hidden inside all of this. Once you sit with it long enough, one that has nothing to do with rockets or gravity at all. For nearly the entire span of human existence, our species looked up at the night sky and saw a ceiling, a fixed, unreachable backdrop of scattered light with no real sense of depth, no clear understanding of distance, no working concept of an edge to search for in the first place. We now know, with real, measured confidence, not just that an edge exists, but roughly where it sits, roughly how far it extends, and roughly what fills the vast, quiet space between here and there. We know this because we built something, sent it outward, and kept listening for as long as physics allowed us to. That alone, regardless of how the rest of the story unfolds over the coming tens of thousands of years, already represents a genuine, permanent expansion of what our species understands about its own home, a home that turns out to be considerably larger, considerably stranger, and considerably more interesting than anyone standing on this planet a few centuries ago could have possibly imagined. Somewhere out past Neptune, past the Kuiper Belt, past every point of light you have ever wished on, 4 small, quiet spacecraft are still moving. They are not lost, and they are not stranded. They are exactly where the physics always said they would be, on trajectories that guarantee, with complete mathematical certainty, that they will one day be free of the sun's grip entirely. They are simply early, unimaginably early, in a journey whose true finish line lies so far beyond any point we can visit or even properly picture that the very idea of watching it end has to be set aside entirely, replaced instead with something closer to trust. Trust that the numbers are correct. Trust that gravity, patient and indifferent as it is, will eventually finish what a handful of engineers and a fortunate planetary alignment started decades before almost anyone listening to this was even born. Trust that somewhere, tens of thousands of years from now, in a galaxy that will look subtly different from the one we know, a small, cold, golden record will finally drift free of the only star it has ever known, carrying a message that none of us will ever know was delivered. Maybe that is enough. Maybe reaching outward was never really about arriving at all. If you found this journey through the true edges of our solar system as strange and as humbling as it deserves to be, take a moment to like this video and subscribe for more journeys into the cosmos. And for now, let the sun's quiet, patient pull hold you here a little longer, safe on this small, spinning world, as the stars keep their slow, unhurried watch outside. Rest now.